Yeah, I'm going to record. Yeah. All right. Sorry for the starting trouble. The topic this time is Bayes regression. So we will, in fact, in the earlier talk as well, we had talked about Bayes rule. And before that, Rajesh had just brought up this subject of Bayes regression. So I thought, why not this topic? So it kind of continues from a little bit from the Bayes theorem or Bayes rule we talked about in the last session or the earlier session of mine. So again, context setting. This is again just 30 seconds so that you guys can, we all can see. So we have to note some of these terms here today when you read up or look up different sites. All these topics, all these words keep coming up. Okay, Bayesian, frequentist, and then priors, posteriors, so on. So that's the reason I just brought it up again. So we'll talk about them again. And on the right-hand side, this is the process framework, just like the software development life cycle. So for every data science engagement, as we said, this is like a life cycle for a data science engagement. So application of Bayes rule, this you have seen earlier before. So I just wanted to again contextualize. That's why I brought it up. So when we have two events, let's say, so or rather when we are studying probabilities and we are interested to predict some probability, let's say a probability of one event has happened, and then we get some additional information, and that information you want to use somehow. Therefore, it becomes like you have one event that is A, and you have another event B, and therefore you are trying to look at using the knowledge or the evidence of the information B. Could you estimate or predict what is the probability of A, the first event, or the prior event, given the event B has happened or occurred? So that's what is PA given B means. And in fact, that is exactly what is the posterior probability. So recalling some of these kind of regression, right? We said regression. So that's the reason I just brought this up. I hope some of these, these three small pictures are kind of visible, though it's looking small. So you see the regression model, yi is equal to beta 0 plus beta 1 x1 or xi plus epsilon I. So this is a linear regression model, right? I'm sure you would have seen this before. So you know about it. So when you talk of regression and linear regression, a simplified version with, if you're having two variables like y and x, so I showed a small picture there, that set of points that show some sort of linear trend in the left-hand side, right? So this one I meant. So you see a trend there. So regression is talking about, those set of points, the relationship between, a quantified relationship between y and an x, right? So this is what you see. So forget this example for a second, but that's what is linear model and a set of points that show a linear trend. That's the reason I put it up. So what happens is in our usual method, what we do is we try to find the best line. That's why the bottom picture there. So when we are doing this, so we draw different lines, a different set of lines, those which pass through as many points as possible. That's one way of looking at it, right? In fact, what is happening is there is a method, in fact, called the maximum or, linear least squares method, which actually uses the maximum likelihood method as well. So under that method, what we are doing is we are computing the parameter, the estimated parameter value. In this case, as you can see, these are the betas. We are trying to estimate the value of the betas in the linear regression. So what happens is So you can go through that in some of the places or videos. But the problem with linear regression are these, on the left-hand side, so that we have a context for Bayes regression. So for now, just ignore the first one, no, not truly Bayesian, but look at the other ones. So a linear regression model, whether it's linear regression when you say multi-linear regression model or linear regression model, these are some of the problems. That is, that particular linear regression model method of prediction or machine learning, it has some susceptibility to outliers. So that means those extreme points can swing your estimation, okay? So the other thing is that it can be sometimes very simplistic, and therefore a linear regression could have some underfitting. Likewise, there may be some problem of overfitting. The other thing is that when you're having multi-linear regression, so I hope you're with me. So what we're saying is sometimes these x's, those explanatory variables on the right-hand side of those equations, right? So those explanatory variables are correlated. So when you are having these correlations, then you have some problems. These are some of the issues with linear regression. So what happens is the model to some extent gets confused by some of these issues, let's put it that way. So far, so good? Okay, so maximum likelihood regression or maximum likelihood method. I'm sure if you have gone through some videos, you would have heard some of these methods, maximum likelihood method. It basically derives our, how do we, using differential calculus used to find the, like a maxima, remember? So maximum likelihood is method that depends on that kind of a mathematical method. So what happens is for a conventional regression, that is the usual regression, we maximize the likelihood function. And by the way, when you say likelihood, well, in English it's a term, right? But in a statistical parlance, likelihood is actually a product of probabilities, okay? So the English word has a deeper meaning in statistics. So what we are doing is we are trying to maximize the probability, which is a product of the probabilities. That is, it's a product. You're maximizing a value there, a function, because you have some experimental data. So probability of getting a value of 1, probability of getting value of 10, probability of value of say 20, right? So you take the probability of all, that is the product of all the probabilities. So suppose you had a dice, right? It's like 6 sides. You have a dice with 6 sides. So you should, maximum likelihood means that you have to take the product of the probabilities. So probability of 1, 2, 3, probability of 2 multiplied by probability of 3, so on, up to probability of 6. So that's the product of the probabilities. So that way I'm saying, so when you have an experimental data, so likelihood is actually product of the probabilities given an unknown kind of value, theta, okay? So that is what is the likelihood. So what we are doing is we are using the product of the probabilities of the probabilities, and then what you're doing is you are maximizing that and differentiating that is with respect to theta. So theta is the parameter of the model. So what happens is you get an estimate for theta. So under the conventional method, what we usually say is that so we assume that theta is unknown. We're trying to find the maximum value, right? So theta is considered to be unknown, but it's fixed. So that is the way we look at maximum likelihood method of regression. So Bayes had a different thought process around it. So Bayes was saying, but should we not maximize probability of theta given the data? See, he produced a very non-intuitive way of looking at things. He flipped it around. Given the data, what is the probability of the value of the parameter? And he's considering theta, which you thought theta to be fixed, right? He's considering theta to be something like a random variable where it can take multiple values. So it's a different very non-intuitive, I suppose, but basically that is the different thought process or a different line we need to take. So here, the unknown parameters may be thought of as random variables that have probability distributions. So that is the way the Bayes regression, that paradigm shift happens from there. So we are trying to look at probability of theta given an experimental data y. Okay, so whereas the maximum likelihood was different, it was simply considering theta to be fixed, and we were composing an equation with all the y's, right, and differentiating with theta, and then we're getting it out. So theta was disappearing, in fact, and a value of theta was being produced, that this value of theta is the so-called value of theta. So that's the difference in methods. Fine. Moving further, so let's look at one small example again. Suppose there is a lab test for a disease. And this lab test, by the way, is very effective. That's why it's saying 95% of the time, it's able to effectively detect the disease. And also we are told that it has a false positive rate of 1%. And the prevailing rate in the population for the disease, and this disease could be anything, say dengue fever, or it could be cancer, whatever. Okay, so this is a nice example. So the prevailing rate of occurrence in the population is 0.5%. And the other two are, it is a probability of the test being effective, and the other one is the probability of a false positive rate of 1%. So given this kind of scenario, we take this test. Suppose I take the screening test and I get a positive result. So the question is, what is the likelihood that I have the disease? So the question is, given these 3 bits of information that the general population has, the prevailing disease risk of 0.5%, and if I take a test, chance of 95% of detection, if I have the disease, and the false positive rate is more like an error, right? So 1%. So what is the probability of the likelihood? What is the likelihood that I have the disease? So this is the kind of question we are trying to deal with in a Bayes rule. Let's look at this example in computation. So do you remember the Bayes rule? I hope so. So this is what is the Bayes rule. So what it does is, if you want to compute probability of one event, D, given an event T has happened, then this is the right-hand side expression. So you can simply, probability of T given is flipped around. The probability of the T given D times probability of D given divided by probability of T. So anyways. So let's carefully define the variables. So let T be the event that I was tested positive when I took the test. Okay. Let D be the event that I have the disease. That means I'm having a disease like fever or some fever, and therefore the doctor told me, hey, why don't you take the test? So that is if I have the disease, then that's the event of having the disease, that I have the disease, D, and event I is the test being, successfully showing the result of positive. So we want to know the probability of D, the disease. I have the disease given that I took the test, and the test was showing a positive result. That's what is P of D given T. Okay, probability of disease given T. That T is that tested positive. So this is the screening test. So what is the likelihood I have? This is what we are trying to solve. So actually, when you look at the Bayes rule and map it down, you will get this. Okay, so it becomes 95% chance that probability of given somebody having disease D and probability of the test being positive. So that is 95%, pretty good, right? Similarly, probability of somebody not having disease, like a D bar. Okay, probability of given that somebody is not having disease and he takes the test positive and he gets the result positive. that chance is very low, 1% only. And probability, as we said, D, prevailing probability in the general population is 0.5%, so D. So if you plug all these values into this Bayes rule, then you get the value here. Actually, it turns out to be 0.32, okay? So somebody may have said, hey, since you took the test and you had the probability of T given D, right? Probability of somebody having disease and having taken the test, T, 95%, right? So somebody would say, hey, the chance that, you have the disease is, very high, 99%. Somebody will say like that. So it turns out that actually in the posterior probability, it turns out to be 0.32. So this again, I've just showed for those who are interested to pick up the tree diagram again. So here the probability is derived as a product. The probability of the intersection T intersection D is simply product of these two values, 0.5% into 0.95. Okay, so that's how we get the value of 0.00475. Okay. You can look at this slide later if you like. So let's talk about Bayesian statistics. So Bayesian statistics, what we do is we systematically use the Bayes rule and combine what we learned from the experiment versus what we knew before we began the experiment. So our previous example, what does it tell us, right? We got to know the effectiveness of the test was 95%, the false positive rate was 1%, and prevalence of the disease as 0.5%. So what we learned from this experiment is basically the results of the test of one patient. So suppose there are multiple patients and therefore you have multiple data points. So then you'd be able to do the posterior probability. So in fact, when you start looking at posterior probability, that is only one instance, right? So actually, this turns out to be that you'll get multiple data points and therefore it will become it's like a probability distribution as opposed to a single probability value, okay? So that's where we are going down to. So again, so just a quick summary of what is the Bayesian versus the frequentist. So frequentists tend to look at probability as a limited or limiting case, as a limit of an experiment. That is, you have a repeated experiment, and that repeated experiment, let's say you're doing a coin toss. So suppose you do 100 times, 200 times, 400 times. The number of times, the proportion of the times you get the heads, when you start taking those values, and you start doing a limit of all those, the mathematical limit, if you remember. If you start doing that, then that limit is a probability. That's what frequentists define probability as. And they say, whatever is the unknown parameter or unknown constant, they consider the parameter to be constant, first of all. And then they say that data, so model parameters are unknown, and data is the random variable. That's what they consider as far as frequentists are concerned. Now, how do Bayesian look at it? Bayesian look at it quite differently, okay? So they consider probability to be subjective. That means based on my degree of certainty in my event and my knowledge, based on that, what is the probability? So they're trying to be very subjective. And they consider model parameters to be random variables. Whereas we thought parameters to be fixed and constant, right? In the case of frequentists. So they consider whatever data you have, data is constant, they think. That means, let's say you have a sample data of 100 points or 100 rows, let's say. So they consider this 100 rows that's all you have. And this is fixed. And what they do is their technique is different. So they try to do some sampling and they try to do some other methods and infer the probability out of that. And they basically do some other methods for posterior probability. So they use different, so that's why they call it as subjective probability. All right, so coming to Bayesian regression. So Bayesian regression means basically on the left-hand side, you're developing the posterior distribution. So distribution, this theta is in fact parameters, all the different parameters. So you're considering parameters to be variable, like a random variable. So given the data y, which you see here, given the data y, what is the probability of theta? What is the probability of all the parameters? What values, what range of values the parameters can take? So that's why it's a little non-intuitive, but try to get the concept. So according to the Bayes theorem, we saw, right, it's simply the product of likelihood function times the, this, we have seen the same expression earlier, right? If you see this expression here, if you see this, right, this expression here is the same thing. It's the same thing, in fact. So except that here, theta is not a single value. Theta is in fact a parameter, all the parameters, okay? And data is y. So probability of theta given y, given the y experimental data, what is it? It is equal to simply the product of the likelihood function times the prior distribution divided by probability of y, the experimental data. So we already know how to calculate the likelihood function, right? We said that it's simply a product of all the probabilities. So that's what is the likelihood function. And also remember here that theta means not a single theta. It's a range of parameter values, a set of values that all the parameters could take. So therefore, the parameters will have different range values. So we make assumption about the PDF or the, about the distribution of y, which is the experimental data. We have to make some assumption. So in the case of the prior, we were saying, right, that the prevailing disease rate to be 0.5%. Or if you're doing some economic theory, right, this supply versus demand, you may say the demand is 1% or 2% based on a theory. So sometimes you have to rely on other methods to get to the posterior probability, okay? So in the case of model parameters, or the theta, so what we're trying to do is the theta could include the parameters. It could be mean, variance, error variance, so on, okay? And we try to understand what was it before we began the experiment and what was it after, okay? So how do we interpret the posterior distribution? Okay, so I hope so far you are with me because it's a little non-intuitive. So what we're getting is the posterior distribution simply it's an output of the Bayesian regression, okay? So what we're doing is, as we said, we're calculating the posterior probability, right? In fact, a set of probability values, and therefore it's a distribution, okay? So given the experimental data, so we are getting the probability distribution given the experimental data. So just like the maximum likelihood estimate, you have to remember it's not that other method simply was calculating one value of parameter, whereas here we are considering the parameters to be a random, like a random variable. So we are interested to compute the posterior probability given the experimental data. Just remember that. And how do we interpret the posterior distribution? Those are some of the aspects we are interested. Voice is not clear. Oh. Thanks for letting me know. So voice is not clear, but I'll go slow a bit. So we need to interpret the posterior distribution, and also we need to summarize the posterior distribution. That is some of the aspects that Bayesian statistics deals with, or Bayesian regression deals with. And if you have heard of confidence interval, so similar to confidence interval, we have something called credible interval. Is it better, Mahesh? Thanks. Okay, this is a quick summary of Bayesian statistics. You can read up later on. So, but basically, probability of theta given data is proportional to the probability of data given theta times probability of theta. Okay, so just it's a mouthful, but just bear with me, so you can read it up later. So let's look at one example of Bayesian regression. I used a package called RStanArm. Okay, there are many packages that we could look at. Learn base is there in R. In Spark also, in Python you have a similar package for Stan. So these are the 4 main steps in Bayesian regression. So what we do is we specify the posterior distribution, and we draw a sample, repeated samples from the posterior distribution. Based on the posterior distribution, we get some values. We try to see how close it is with the prior. We try to make some evaluations of the model after the step 2. And finally, we do manipulations, the step 4, analyze the manipulations of the predictors. So here is one example. I try to make it as simple as possible. So this is a generalized linear model example. And we can go through that. So this model, so we are having a situation where, yeah, are you all okay? So continuing. So we have a survey. In that survey, we are trying to get the respondents' data, whether they agree or disagree with respect to a conservative statement about role of women in society. So that particular data has been, the survey data has been modeled using the GLM method. Just like linear regression, just like linear regression method, you have something called generalized linear model. So in a linear model, I don't know whether you recollect, the y and the x's, they all have to be normal. The variances have to be constant. The error of variance has to be 0. There are a few assumptions like that. Whereas in the case of generalized linear model, there are some relaxations. That is, it need not be normal. Okay, so just as a context. Okay, so here on the left-hand side, this, if you see in a generalized linear model, so you are doing this probability of theta given y, that kind of a thing. If you see on the left-hand side, so if you see, though it looks very mathematical, try to look at the simple side to it. And this is simply the product of this is the prior probability, the f alpha beta, f of f, this is simply the product of the priors, and this is the likelihood probability. Okay, so this bit, the second piece is the likelihood, the first bit is the prior, and this is a joint probability. So that's exactly what we are trying to do. So in this model, we are trying to predict eta. Forget all these letters, but basically we are on the right hand side, you're trying to make an expression out of alpha plus a parameter times education and gender, beta 2 times gender. Okay, so we are trying to make a generalized linear model. So that's what is the eta. This is Greek letter eta. So this is our so-called y. So that was the step 1, or rather, okay. So now drawing from the posterior distribution. So what we have done is eta, I have just brought it out as a product of the likelihood. Okay, so just for your, just brought this expression out here. This is the likelihood, in fact. Normally what you do is when you get any data, as you know, we have to do some visualization. So I did a little bit of visualization, whether you are able to see, I'm not sure. You can see by gender, you can see the education. What are the distributions? So for example, you see males, the number of years, okay, on the left-hand side. So 5, 10, 15, the number of years of education. So in the case of males, it's quite kind of spread, right? That's what you see, the blue. In the case of female gender, you see that the range is far wider. Okay, they have spent lesser than 5 years as well as all the way till 15 years. Whereas in the case of males, they have the the people considered in this study, respondents, they only had a range of the education years between maybe 6 onwards till about say 12. Okay, so just normally you have to do a little bit of visualization. I didn't do much, but just for your information I'm saying. So here in the generalized linear model, it's a simple, so it's a GLM, and this is the Y dependent on education plus gender. So it's a very simple model as an example, where the data is this women's role. It's a small data from this package HSOR. I'm not sure whether it's there in Python, but this is a freely public data set. So what we are getting is we are getting a generalized linear model in this variable, okay, as an output of the GLM function. That's what you specify here. And then we have to specify in the case of R, logistic regression, okay? So when you do the summary, you get these values. So you can see that education has, education is, because the probability is so low, right? So therefore it's very significant. Likewise, in the case of gender, you see it's not significant, in fact. Okay, so it's 0.8. So this is a model that we derived from the posterior. So under this method, there's a sampling that goes on. What it does is so based on the sampling under the STAN package. That's what you see here. You have to provide 2 chains, and I gave a seed of 1, 2, 3, 4, 5, and I assumed a prior distribution of student. So keeping student as prior distribution maybe is out of scope for now, but we can discuss offline if you like. But basically, in R, we have to load the library and simply do the STAN GLM on that model with all these parameters, families, binomial, with logistic, prior distribution of students, so on. But you have to specify chain is equal to 2, and so that 2 chains. If you do chain equal to 4, obviously more. So you get a lot of sampling, so like Gibbs sampling, if you have heard, some of these methods underlying which are invoked. Based on that, you get a new model here. That's what you're getting, where you get the estimates also. This is the median estimate, and this is the mode, if I remember correctly. So you get MAD, and you get the median. So unlike the frequentist, so let's read up this. Unlike the frequentist confidence intervals, which are not interpretable in terms of post-data probabilities, here we get 2 other values, actually 95%. 95% probability of beta being, unfortunately we can't read what is here, so just bear with me. Alternatively, we could say that, in fact, in this test, what we are doing is we are trying to check whether the betas are 0, and we find that beta 2 is not 0. Beta 2 has a value, and therefore it's 95% probability has been given for that. So this is a generalized linear model. Okay, so these estimates are quite similar to the maximum likelihood estimates, just for your info. So here we are able to get some additional graphical information. We are able to plot the proportion of the people who agree versus the years of education for both male and female. And in this diagram here, we are able to see, if you see in the middle, okay, there's a closer, these points are closer to the middle, right? So if you see all these points, they're closer to the median. So likewise here also. So you see more points, whereas here you see several points out of the box, right? This is a box plot. So what you're saying here is between 6 and 16, between 6 and almost between this and some 16, okay, roughly here. Between that 6 and 16 years, you have a reasonable estimate here. This is a closer fit of the model. That's what we can say here, okay? Whereas for the years below 6 and greater than 16, well, we can also say that it's not very good. Okay, so that's the other interpretation. And here also we are able to produce. There's a under the Bayes regression, we use a package by name LOO, LOO. So leave one out cross validation. For that leave one out cross validation, we are able to do. We get two models. We're able to produce two models, and we are able to compare these two models with the LOO package, LOO package. Okay. So when we see these graphs on the right-hand side, they are showing a few moderate outliers. Okay, so 30, some of these values that you see here, these data points, 30, 34, they're interpreted as outliers. I too am still learning some of these, but little bit of that intuition I thought I would share. So just like if you remember the AIC criteria, so you have LOOIC criterion. So just like AIC criterion for selecting the model. So in that, by that regard, this model seems to be a reasonably good model. Further, this is another estimation we got for the posterior probabilities. Okay, so what we see here is that out of 100 women who have college degree versus 100 women with only high school, we expect only 20 fewer college educated women to agree, and they lie in this range between, the differences lie between 16 and 24. Okay, this is what is being depicted here in this graphical in this output, in fact. So what we are saying is, note, let's read up this a little bit, we'll get more intuition. We want agree and disagree to sum to the number of people we want to predict for. The values of agree and disagree don't matter so long as their sum is the desired number of trials. We need to explicitly imply the number of trials like this because our original data are aggregate. If we had Bernoulli data, then it would have been a given, but we wanted to predict for a single individuals. So these are the 4 steps of Bayesian regression example. So I'm just kind of summarizing here from here. Hope so far you're with me. So in a Bayesian conceptual framework, what we do is we have 3 things going on. So we have response variables, inference of the relationship, and the explanatory variables, right? So we have to specify the probability distribution of the likelihood for the data, response and the explanatory variables. Then we have to specify the form of relationship between, we have to assume a form of relationship between y and x. So that's why between response and explanatory variables. And also we have to use some expert opinion or a theory to specify the probability prior distributions for the regression coefficients. So these are the 3 steps for the conceptual framework. So in summary, what we have done here is, so we learned a little bit of Bayesian theory. It is a little bit non-intuitive, but it has to a different way of thinking, in fact. And so we have also estimated a relevant model using this R-stan arm package in R. We looked at some of the plots and the model output. We also looked at some functions output, functions of the model output. So if you like to take some sort of, some resources, so here are some of the web resources I put down for R-stan arm. There's a lovely book written by Gelman, in case you would like to look in as well. And there are a few good YouTube videos as well that give you some idea about how we can use R-stan arm. So the potential is there because Bayesian nowadays, I'm hearing a lot of these Bayesian methods are being used in marketing. So it seems, though non-intuitive, but we need to figure a way out of trying to apply some of these Bayesian techniques So with that view, I thought this Bayesian topic may be of interest. With this, I finish the presentation. Any questions or comments?
Raj, I would like to know, like, is there any difference in the model performance when compared to frequentist approach? Or have you tried that? I'm not sure.
Good question. I didn't try, but basically it's a very, in the case of, you will get a slightly different result, definitely, for sure. We'll have to figure out how to compare the results of these two models, like a frequentist method. Suppose you get because you will get one estimate, right? For the, let's say, the maximum likelihood method, you will get one value of mu, and you don't consider any other possibilities that mu could be different or a sigma can be different. So sometimes it's non-intuitive when we're trying to combine. So it's a very good question, I would say, but I'm not answering your question, I think. But that's the way to kind of, I think it's important to expand our view from that angle, I think.
Okay, thanks a lot. I'll also check on that.
Yeah, it may be a good area to figure out, yeah. Any other questions or comments? Okay, so thank you again. Feel free to reach out to me. So even I'm learning about Bayesian regression, and I think it has potential from what I see and hear. Bayesian, there are a lot of now kind of Bayesian applications in marketing. So a lot of business applications in marketing, those guys are using Bayesian. So if we are able to intuit, we can be very different in terms of our solutions to a customer, I think. So, but so that's it. Thank you so much. Have a wonderful weekend. Yeah.
Thanks, Raj.
Thank you, Pratik. Thank you, everyone. Bye.